Good evening, everyone. Welcome to Byju's Exam Prep IS. First, a sound check, video check. If everything is fine, let me know before we start the session. All good? Wonderful. So I see good evening, good afternoon, everything here. Very good. So depending on your time zone, good evening, good afternoon, good morning, wherever you are. Okay. So let's begin with our session. So yesterday important radioactive elements. So there was some confusion in the team. They had an older document that I had given them last time. So by mistake, they had uploaded that document. So today I have passed on the new document to them, and I'm sure that it will be shared to you while the classes go on. In some time, it will be shared with you, and it will be available as additional notes. So don't worry about this. Right. So yesterday, we had started with our second chapter, that is space technology, and this is where we continue today. Now, we had stopped at the basic understanding of the formation of the universe, where we understood what the Big Bang theory is and the various aspects of the Big Bang theory. And if you remember, I had discussed with you that there are two theories, one being the Big Bang, which is the most widely accepted theory. But apart from that, there is another theory where we see a lot of discussions around. And that theory is the string theory. Now, in case of string theory, when it comes to string theory, understand what exactly is string theory and why are we calling it as string theory. Now, string theory tries to explain the universe in a very different way. What it says is that the entire universe and every particle in it, all the forces and energy particles, all the matter particles, they're all made of very tiny strings. That even protons, neutrons, electrons, etc., they're all made of very tiny strings. And various different types of vibrations in these strings, they produce different types of particles. Just imagine any stringed music instrument, for example, a guitar or a sitar, violin, etc. So when you try to play a guitar, what happens is that you create some vibrations in the strings, right? You create some vibrations in these strings, and the vibrations in these strings, they produce different musical notes, correct? They produce different musical notes. Similarly, when we talk about the string theory says something similar, that vibrations in these very tiny strings, they create different types of particles. So each and every particle, every kind of matter and force that we know of, they're all made of these very, very tiny strings. And these are very tiny. I mean, these strings are so tiny that they're not observable. You cannot see them under microscope. There is no instrument that we have currently which can actually see these tiny strings. So that is one of the reasons why this string theory still remains theoretical, and there is no practical, uh, you can say, and practical implementation that we have seen, or we haven't really observed it yet. So that is where there is a drawback to this theory, because until now it remains a theory and there is nothing that proves this theory to be correct. But even if that's the case, why are we still talking about string theory? Why is it still a theory which interests a lot of scientists and engineers across the world? Understand what it says. So, string theory says that all the particles, that is matter and forces, are made of extremely tiny strings various or other different vibrations in these strings produce various particles. All right. So this is what string theory says. So now that's why when we look at string theory, it tries to explain the fundamental level of the universe in terms of vibrating strings rather than particles. So everything, it says that everything is made of these tiny particles. Now, why are we still discussing about string theory even though we do not have any substantial proof of this theory, or there is no practical observation of this theory, yet it remains a very crucial theory? Why? The reason is this very thing called as theory of everything. Now, when it comes to theory of everything is a concept where we are saying that we will be able to get or explain every fundamental force in one single equation. Now, very first thing, what do we mean by fundamental force? There are four fundamental forces. Can you name them? Can you tell me which are the four fundamental forces? Anyone who knows? All right, gravitation is one, that's correct. So, one is gravitational force. What else? Electromagnetic force. All right, correct. Electromagnetic force. What else? Yes, strong nuclear force and weak nuclear force. So, another one is strong nuclear force, and then we have weak nuclear force. So these four are called as the fundamental forces. Now, why are we calling at them as fundamental forces? The reason is that these are the four forces which are there in the entire universe, and every other force that you know of your or you have heard of, they are one form or the other of these four fundamental forces. So that's why these four fundamental forces, they are the most important forces, and they are the ones which make the entire universe. And every other force that you've heard of, they are actually one or the other of these four fundamental forces. That's why they are called as fundamental forces. Now, why? What is theory of everything? Theory of everything tries to explain all the four fundamental forces together. That in one single explanation, in one single equation, it tries to explain all these fundamental forces. So that's why this is called as theory of everything, because it is trying to explain everything or every fundamental force. Now, string theory, if proved to be correct, sometime, let's say in the future, if it is proved to be correct, then it becomes a very important candidate for proving theory of everything. That string theory would be able to explain theory of everything. It will be able to prove theory of everything to be correct, which until now we haven't been able to do. All these four forces are seen as different forces. There is no single direct relation between all of them. So that's why right now it remains a mystery. But if string theory is proved to be correct sometime in the future, then in that case, perhaps theory of everything also will be proved to be correct. There is one scientist whose name we always take when it comes to this concept of theory of everything. Do you know who? Do you know the name? I think somebody already had written the name. Yeah, Pathan, you had written the correct name. There is one scientist who has given huge amount of time, I mean huge amount of his life, to trying to prove theory of everything to be correct. Yes, it is Stephen Hawking. So Stephen Hawking becomes very, very crucial when it comes to the understanding of the four fundamental forces, and that's why he has been somebody who has been associated with the understanding of this. So that's why it becomes very, very crucial from this perspective. Now look at this question. Okay, one more thing, sorry. When we talk about fundamental forces, these three fundamental forces, strong nuclear force, weak nuclear force, and electromagnetic force, they together They are called as standard model of physics. They are called as standard model of physics. All right, they're called as standard model of physics. Now, why they are all taken together and we do not include gravity in it? The main reason is that compared to the gravitational force, these three forces are immensely strong. These three forces are way stronger as compared to the gravitational force, and that is the reason why when we talk about these fundamental forces, we talk about these three together as the standard model, and we do not include gravitational force in it, because gravitational force is a very weak force as compared to these these three fundamental forces. So the strongest of them all is strong nuclear force. Then after that we have electromagnetic force. Then we have the weak nuclear force, and then lastly we have the gravitational force. Right, so this is the magnitude in the order of their magnitude. This is the strength of these forces. Now there is this one question that has been asked in your paper in 2017. This question was asked. It's a fairly simple question. Please read the question. I'll start the poll also for you. All right, so I hope you have read the question. I'm launching the poll. Please mark your answers. Wonderful. 79% of you have marked A, which is the correct answer. Well done. So correct answer is A. The terms event horizon, singularity, string theory, and standard model are sometimes seen in the news in the context of. So we've not discussed yet what is event horizon or what is singularity. We'll discuss that a little later. String theory and standard model we discussed, right? B is study of the solar and the lunar eclipses. We did not discuss anything about the eclipses. Placing satellites in the orbit of the Earth. We did not discuss anything about placing satellites. Origin and evolution of living organisms on the Earth. So it's not only about living organisms, but everything in the universe, right? This is what string theory is about. Every matter, every particle in the universe. So that's why observation and understanding of the universe is the correct answer. Moving on, now we look at all the different types of celestial bodies. The first celestial body being a star. Now, star basically is a celestial body that generates light by nuclear fusion and is held by its own gravity. And I'll just add to it, it gets its spherical shape. It gets its spherical shape due to gravity. All right. So gravity gives it its spherical shape. Now, in this case, when we talk about a star, we know that there are nuclear fusion reactions that occur at the core of any star. And this nuclear fusion is the source of all the heat and light that is generated by any star, including our own sun, right? So that's why nuclear fusion reaction, that is one very important criteria for something to be described or defined as a star. And at the same time, they must be held by their own gravity, which gives them a kind of spherical shape, even if not exactly spherical, almost spherical. So that shape that they get is because of gravity. The kind of stability that gravity provides because of the exertion of this force from all the directions, that gives it the spherical shape. Now, when it comes to any given star, first we need to start understanding how does a formation of a star happen. A formation of a star, remember that the originate origin of the star is from a nebula. Now, what do we mean by nebula? Nebula is the most widely used screensaver and wallpaper in this world. Uh, but that is not the definition. Nebula basically is a bunch of dust and gases which are scattered in the universe. But yes, nebula, I mean, if you go and do a basic internet search, if you look at Google Images or Bing Images or whatever search engine you use, you'll find that there are exquisite images of different types of nebula, different nebula that we have observed, and they all look very beautiful. And that's the reason why they are the most widely used screensavers and wallpapers in the world. Now, so nebula, what do we mean by nebula? Nebula is nothing but clouds of dust and gases. All right, these are clouds of dust and gases. So, meaning that they can have very small dust particles, hydrogen gas, helium gas, some of the other ionized gases as well. So, they can be all present in a given region, may not have a specific shape, may not have a defined shape. Sometimes they do have defined shape, sometimes they don't. So, for example, here as you can see that it doesn't have a defined shape here, right? So, there are various different nebula, they have various different shapes, and these are nothing but clouds of dust and gases which are scattered in a given region. Scattered in a region. Now, in this particular scenario, when it comes to nebula, nebula become the origin. They become the origin of any given star. So what happens is that gravity will start to pull all these gases and dust particles towards each other. And in that case, what happens is that a small ball of mass gets created. Now, as this small ball of mass is created, obviously it has its own mass. So that's why it has its own gravity. So now it starts to pull everything else which is there in the surrounding. So it starts to become a star. It starts to assume the shape of a star. First, it will be called as a protostar, which is a small size star. And then after that, we see that the center of this cloud becomes very hot and nuclear fusion reactions start occurring. And this is where it starts to become a star and starts to release very huge amount of energy and becomes a star which shines with its own light. Now, in the context of a star, it is also very, very important to understand the life cycle of a star. And let me start with a question. When our sun dies, it will convert into a black hole. Launching the poll very quickly. I'm not going to give you a lot of time to answer this question. When our sun dies, it will convert into a black hole. Is it correct statement or wrong statement? Hmm. So 55% of you think that it will convert into a black hole, 45% of you think that it will not convert into a black hole, and 45% of you are correct. Our sun will never convert into a black hole. And let's try to understand why. So what we know is that origin of a star is nebula, right? Origin of a star is nebula. But there are two types of stars that can be formed. Either an average star or a massive star. Now, what do we mean by an average star? What do we mean by by a massive star? An average star is a star which has mass up to 1.44 times that of the sun. So if you assume our sun to be of 100 grams, then any star which has a mass up to 144 grams they will all be called as an average star. All right, they'll all be called as an average star. Now, in this context, when we talk about a star, average star, that's why our sun itself also is an average star. Our own sun in our solar system is an average star. And above this mass, all the stars that we have, they are called as massive stars. Now, for an average star, when it starts to run out of its fuel, when it is not capable of conducting nuclear fusion anymore, then it starts to convert into a red giant. Now, red giant, giant means that it is much bigger in size, so it starts to expand. It is much bigger in size in that sense. And red because the surface temperature starts to decrease, because now it is running out of its fuel. So that's why the surface temperature is actually decreasing. So that's why it converts into a red giant. And then it finally converts into a nebula called as planetary nebula. Now, planetary nebula has nothing to do with planets, all right? Nothing to do with formation of planets or anything to do with planets, just that it is kind of disc shaped, so it was named as planetary nebula. Scientists did that, they should not have done it, but beyond what I could do. So, planetary nebula. So, they would convert into a nebula again, and from here on, they convert into a white dwarf. So, an average star at the end of its life would convert into a white dwarf. So that's why our sun would convert ultimately into a white dwarf. All right, our sun would convert into a white dwarf. Now, when it comes to the massive stars, when they start to run out of their fuel, first they would convert into a red supergiant. Then, after that, they become very highly unstable. The core of this red supergiant becomes very highly unstable, and an explosion happens. Explosion happens at the center of the star, and this explosion is called as supernova. So, what is supernova? Supernova is an explosion. It is an explosion at the center of a red supergiant. All right. So explosion at the center of a red supergiant is supernova. Now this supernova is very strong, very violent, and supernova are the largest sources of neutrinos. Remember we discussed about neutrinos yesterday, that they are chargeless and almost massless particles. The biggest source of neutrinos in the universe are supernova. So whenever supernova happens, it leads to the formation of huge amount of, so supernova, they are the biggest sources of neutrinos. Right? They are the biggest sources of neutrinos. Now, after supernova, there are two things that can happen. Either this massive star converts into a neutron star, all right? Either it converts into a neutron star, which is, these are the smallest types of stars in the universe. So either they convert into a neutron star, or they convert into a black hole. All right, or they convert into a black hole. Now, when would they convert into a neutron star versus when would they convert into a black hole? It largely depends on the mass of this star. Generally speaking, what we have seen is that if the mass of the star is more than 5 times the mass of our sun, if it is more than 5 times the mass of our sun, then in that case it has higher chances of converting into a black hole. And if it is up to 2.5 times, almost up to 2.5 times, then the chances are higher that it converts into a neutron star. All right. So in case of massive star, in case of massive star, up to 2.5 times mass of sun, chances are higher that they convert into a neutron star, and then more than 5 times mass of the sun, it means that it has higher chances of converting into a black hole. Now, what happens between 2.5 times and 5 times? We don't know. This is something which is also called as the mass gap between 2.5 and 5. This is called as the mass gap because we do not have a proper idea about what happens in this range. Whether it converts into a neutron star or does it convert into a black hole. We do not really have a very concrete idea of what happens in this mass gap. So this is what the life cycle of a star is. Let me give you another question. This was also asked in your paper back in 2009. Launching the poll for you. Please mark your answers. Hmm. So 34% of you have marked B, and actually B is the correct answer. This number 1.44, this number 1.44 is also called as, if you have heard of this, it is also called as Chandrasekhar limit. This number 1.44 is also called as Chandrasekhar limit because it was Subramanian Chandrasekhar, an Indian origin scientist, who had proved it for the first time that if the stars have mass less than 1.44 times the mass of the sun, then they end up as white dwarfs and they do not convert into a black hole. So he was the one who proved it, this theory, and that's why this number 1.44 was named as Chandrasekhar limit. So that's why the correct answer will be B. Now coming to the understanding of the black hole. But before we go there, if you have any questions from whatever we have discussed in the last half an hour, any questions from here? What is the difference between strong nuclear force and weak nuclear force? So, see, when it comes to the strong nuclear force is more or less that force that we discussed, which is trying to bind all the particles together, where it is ensuring that none of the particles get out of the nucleus. That is the strong nuclear force. The weak nuclear force largely defines the forces between the individual particles. The force between protons and neutrons, between neutrons and neutrons, between proton and neutrons. So there are particles which are called as gluons, and these gluons, they basically also define these different types of particles, the subatomic particles, which are making these particles like protons, neutrons, and electrons. So, for example, we have quarks. So these quarks, there are different types of quarks, and they actually lead to the formation of protons or neutrons, etc. So these forces that are there at the subatomic particle level, they are the weak forces. Drawbacks of the string theory. See, when it comes to string theory, the main problem with it is that it is too complex to be explained. There are a lot of things which are assumptions because it becomes very difficult for us to even define that how exactly do we get to uh, what we are trying to explain. So that becomes a major drawback, that explaining it practically is a big challenge. Uh, then what is white hole? See, white hole actually is not an actual concept, but rather a hypothetical concept. And it is a concept where we say that it is just opposite of black holes. We'll just discuss about black holes, and where we'll discuss that black holes, they trap all the light, and they trap all the particles, all the matter in the surrounding. In case of white hole, we say that it is a hypothetical scenario where this is an area that would emit light. It would emit light and it would emit matter. That is what the concept of white hole is. But remember that it is a hypothetical concept. Electromagnetic forces mean electrostatic and magnetic forces both. Is it right? Yes, it is perfectly correct, because electrical properties and magnetic properties are linked. You might know about this, that wherever you have electricity, electricity can induce magnetism, and magnetism can induce electricity. So that's why, because these are concepts which are related to one another, that's why these are called as electromagnetic forces. So you are correct. Please explain white dwarf again. See, white dwarf is a very small sized star, and it's a star which is formed whenever an average star dies. Whenever an average star, like let's say our own sun, when it dies, it will convert into a small sized star, which is called as a white dwarf. And that's why dwarf meaning that it is very small in size. And white, because white is a color which is associated with extremely high temperature. So it is a kind of star which has a very high temperature, and that's why it is called as a white dwarf. Where the black hole sun before I not sun but rather different stars, bigger stars. Please show previous slide. This is the previous slide. What is string meaning? See, string meaning, I mean string, I mean, you have strings, for example, let's say in the guitar, you have different strings. So those strings or wires, they are the strings. Still today, star formation happening. Yeah, star formations will keep on happening every day, every second, I would say, all across the universe. The stars that we are able to see from the Earth, they are massive or average. Many of them are massive, many of them are average. It's a mix of all. In formation of star, nebula have scattered particles, not really scattered, but you can say a region where it's not a well defined shape or a well defined object. It's like a region where you have a lot of dust and gases. So that is what uh, nebula is. Thank you for including all current affairs in your lecture. Yeah, I unfortunately or fortunately, let's say, science is a subject that you cannot read without current affairs. All the recent developments become important. So without that, it's not a subject like history where you are discussing something of the past. It's something which is happening every day, and yet that's where current affairs in general becomes very crucial in this subject. Please explain red supergiant. Didn't get it. Red supergiant. Just break this. Red meaning because it is red in color. Why is it red in color? Because red color signifies low temperature. So it has very low temperature. That's why red. supergiant. Why supergiant? Because they are massive, they are very big. That's why supergiant. Stars can have protons. Yeah, stars will have every particle. Do we have to learn all these small facts about scientists? No, not small. I mean, this is not a small fact. uh, Subramanian Chandrasekhar, he completely changed the understanding of the star, because until then it was believed that every star, when it dies, it would convert into a black hole. But he proved it that no, they do not convert into the black hole. Not all the stars convert into the black hole. There is a specific condition, only then they convert. So it's not a small fact. Do we have to write all the printed question in our note making? Not necessarily. It depends on your process of how you go about it. Saptarishi star concept is real. Yeah, Saptarishi basically is a constellation of star that we can actually observe. So yes, the white dwarfs reconvert into a star, very unlikely. Is interstellar accurate? If you're talking about the film, because although it is science fiction, but even in science fiction, they have tried to be as close to whatever we know as possible. Right. So let's come to the next topic, and this is black hole. Now, two terms that we have here: black hole. Why black? Why hole? Why is it being called as black? Black signifies absence of light. So this is an area, this is a region in space which is completely dark. That's why the term black. And the second term is hole. Why the term hole? Because it's like a well. Just think of a well. It's like a well. So that's why it is a hole. And at the center of this well, it has a very strong gravitational force. It has a very strong gravitational force, and it's so strong that it can basically make every other object or any celestial body in the vicinity to fall towards it, to fall towards the center of it. And that's why it's a very, very strong gravitational pull. Just imagine any well. All right, suppose that you see a well, and there will be a boundary that you have all across the well. If you cross that boundary, what happens? You fall into the well. Don't try this at home. So similarly, when it comes to any black hole, the black hole also has a boundary, which we'll discuss a little later, is called as an event horizon. So this event horizon is something like a boundary of this black hole, and anything that crosses this boundary will fall into the black hole. Now, when it comes to black holes, it has been very, very difficult for us to even observe a black hole, because it is signified by absence of light. There is no light. So how do you observe? How do you take a picture? How do you take a photograph? Because even if you take any photograph, even if, let's say, you pick up your camera or if you pick up your mobile phone and you want to click a picture, you need light there. If it is completely dark, your phone perhaps will not be able to take the picture. Correct? So something similar is happening here as well, and that's why for a very long time we could never take a picture of a black hole. We could never observe a black hole. But black hole was observed by lack of light, various different kinds of very violent movements, etc., that would signify the presence of a black hole in a given area. But otherwise we would not be able to take a picture, we could not take a photograph of this black hole. Now, when it comes to black hole, that's why this picture that you see right here, this was the first picture ever taken of a black hole back in 2019. In 2019, with the help of Event Horizon Telescope, a program called as Event Horizon Telescope program. So with the help of this Event Horizon Telescope program, we were able to take the first picture of a black hole. Before that, if you go today and just go do a basic random Google search, you'll find that there are wonderful pictures of black holes that you will see all across. That these kind of pictures is what you will see. and wonderful pictures all across. But unfortunately, the first picture that we had taken of a black hole looked very different from our imagination. So our imagination was very different, and the actual picture that we got from uh, this Event Horizon Telescope was very different. Now, this picture that we got, this first picture that we got of a black hole, it's of a black hole called as M87, or also called as Messier 87. So this M87 or Messier 87, uh, this black hole was the first picture that we ever took of any black hole. Now, in this particular scenario, when it comes to this, when we talk about this Event Horizon Telescope, it is not one single telescope, but a bunch of telescopes which has been placed at various different locations. And all these together are trying to take the picture, and ultimately they were able to take the entire picture of, still you can say that it was not of a black hole, but rather of the event horizon. If you look closely, what do you see? You see that the center is still not visible. Correct? The center is not visible. What you see is the boundary. That's why it's the event horizon telescope, because we have seen the event horizon of the telescope. We still haven't seen the center of this black hole. So that's why when it comes to black holes, we say that these are places in space where pulling force of gravity is so strong that even light cannot escape. Right? Even light cannot escape. And collapse of big stars, they cause supernova, which may result in the formation of black hole. And just remember, may result. It's not necessary that they will always form a black hole. That is what we discussed. And the M87 was the first picture of a black hole that we ever took, and this was taken with the help of Event Horizon Telescope program. Now, after this, there is the second picture also that we have taken of our own black hole that we have in our Milky Way galaxy, which is Sagittarius A star. So it's a supermassive black hole called as Sagittarius A star. So in 2022, we took the second picture also, and this is the picture of another black hole, and this is a black hole which is very massive, very massive, because compared to M87, which is a much smaller black hole, Sagittarius A star is located at the center of our Milky Way galaxy, and it's a supermassive black hole, and we took this picture in 2022. So typically a black hole looks like this, that you have an event horizon. It's just like, as I told you, it's like a boundary, and this is the boundary of the black hole. And if so, this is like the boundary of the black hole. And if any object, any celestial body, even light, if it crosses event horizon, it falls at the center of the black hole, and the center of black hole is called as singularity. Singularity basically is the center of the black hole. So event horizon is the boundary, and singularity is the center of this black hole. So if anything crosses the event horizon, it will simply fall towards gravitational singularity. And that's why even light cannot escape. We say that even light cannot escape. Why? Because even light particles, although they are so small, they are so tiny, they have such a less amount of mass, yet they are pulled by the strong force of gravity that resides in the black hole. So just imagine the kind of energy, or rather the kind of force that is being exerted by this very small region called as the singularity of this black hole. Okay, I have a very interesting question for you. This was asked in Kaun Banega Karodpati for 25 lakh rupees. What kind of body is Sagittarius A star located in the center of the Milky Way? I hope you get it correct. I am launching the poll for you. Hmm. So 92% of you have marked A, which is the correct answer. So congratulations to every one of you who have won rupees 25 lakhs. Please don't ask me for this money. But this actually was a question that was asked for rupees 25 lakh in Kaun Banega Crorepati. Hmm. Now, coming to another topic, that is gravitational wave. Another topic that has been in the news for quite some time, at least since 2014-15, we have seen that constantly it has been in the news. And gravitational waves. If you look at the words itself, you will get some understanding of what gravitational wave should be. Gravitational wave, meaning that it must be a wave that is gravitational in its origin, right? It must be a wave that is gravitational in origin. That's why these are called as gravitational waves. So now when it comes to gravitational waves, these are ripples in space time. These are ripples in the space time whose existence was predicted by Albert Einstein back in 1915. And when did we observe the first gravitational waves? Almost 100 years later. It got the Nobel Prize back in 2014. So just imagine that this person figured out gravitational waves almost century ago without having any sophisticated computers or any instruments or anything that we have today for getting all the observations right. And this person was able to do everything without using anything as such. Now, gravitational waves. When would a gravitational wave be emitted? Whenever there is anything very violent, anything which is very massive, any very massive event in the entire universe, it can lead to the formation of gravitational wave. Now, what do I mean when I say something very massive? Something very massive, very highly energetic, very violent. What do I mean? Supernova, extremely violent, merger of two stars, merger of two black holes, collision of two galaxies. All these things do happen, and all these things, they are very massive events. So wherever you have any massive event, without any doubt, a gravitational wave will be emitted out of it. Gravitational waves will be created out of these kind of events. So caused due to violent and energetic events like colliding of black holes, supernova, colliding neutron stars, even galaxies, merger of galaxies happen many a times. So all these kind of events, they will lead to the formation of gravitational waves. Now, does it mean that the smaller particles, they do not form gravitational waves? Even they can, but they will not be observable. Just imagine something. Let's say you have a football goal post, all right, and you kick a football towards the goal post. What happens? The net that you have in the goal post, it will form a wave, right? It will start forming a wave because with very high energy, a massive object was kicked towards this net. Now take two things, right? On one hand, suppose that you have a football which is made of iron, which is very heavy, made of iron. And on the other hand, you have a very small stone. Suppose you have a very small stone, a pebble. Let's say you throw a pebble towards this net. Even if it collides with the net, what happens? Even if it creates waves, you perhaps will not be able to observe that wave, right? You will not be able to observe that wave. But let's say when you take that football made of iron and you kick that football made of iron towards the football goalpost, what happens? First, you break your leg, but then when it goes and collides with the net, it creates waves which are very violent. So, something similar happens with gravitational waves as well. That when you have gravitational waves which have their origin in some very massive events, they can be seen millions of kilometers away. They can be seen from millions of kilometers away. And that's why we have been able to observe these gravitational waves here on the Earth, because they have come from very massive events, from events that were very highly energetic and violent. And that's why they have traveled millions of kilometers and they are observable here on the Earth. Now, the first time that we were able to observe the gravitational waves was with the help of Laser Interferometer Gravitational Wave Observatory, or LIGO, which is there in the US. And this is where the first observation of the black hole happened almost a decade back. Now it became very crucial because this was the first time that we could actually detect a gravitational wave. Until now, we had never detected any gravitational wave. And today, what we see is that India is also developing something called as Indigo LIGO. So, with the help of LIGO, we are developing our own gravitational wave observatory here in India. And and that's why this was actually, sorry, I forgot to bring that news article. There was an article almost 5 6 months back that now this observatory, that is Indigo, now finally budget also has been allocated to it. Announcement was made almost 6 7 years back, but now budget also has been allocated to it so that we can start the construction of this gravitational wave observatory. So that's why we see that now we are moving in a positive direction in this particular scenario. Read this question. I'm launching the poll for you. Please mark your answers. I'll be right back. Wonderful. 89% of you have marked B. It's a very good day. All the answers are correct. So 89% of you have marked B, and this is the correct answer. The question says, recently, scientists observed the merger of giant black holes billions of light years away from the Earth. What is the significance of this observation? Now, we are talking about merger of giant black holes. And what did I tell you? That whenever something like this happens, without a doubt, every time gravitational waves will be formed. Now, this happened in December 2018. That scientists observed merger of giant black holes, and that's why this was actually a current affairs question. But do we need current affairs to answer this question? We don't. And you actually will see that there are some questions many a times every year, rather, I would say, in your question paper, where although the question that they have asked is in the context of current affairs, but to answer that question, you perhaps don't need current affairs. Many a times you'll be able to solve that problem, solve that question, if your basics are correct. If you've understood the concepts well, you'll be able to answer them. And that is precisely what we see in a question like this. So that's why the first one is Higgs boson particles were detected. Now, Higgs boson has nothing to do with giant black holes. Higgs boson are at particle level, and they lead to the formation. They are required for the formation of different particles. So that's why nothing to do with giant black holes. C says possibility of intergalactic space travel through wormhole was confirmed. This has never been confirmed outside the movies. If you've seen films like Interstellar, they have confirmed it, but beyond that, it hasn't been. It enabled the scientists to understand singularity. Now, again, although we are talking about black holes, but it was not about singularity, because singularity is something that we have fair idea of. So it's not that they understood singularity because of this event. So correct answer, that's why, is B. Now, coming to the sun. Now, sun also, we know that it is a star. It is an average star, right? it is an average star, and it is also called as a main sequence star. Just know it as a fact for your prelims examination that average stars generally they are called as main sequence stars, and that's why this is also a main sequence star. And it holds the solar system together, keeping everything from the biggest planets to the smallest particles of debris in their orbits. So it is the center of the solar system. It is what leads to the formation of the solar system, or rather having this solar system at the first place. So that's why it becomes very crucial from this perspective that we have this sun. Now, when it comes to the sun, first let's try to understand the various regions that we have inside the sun. So you have the core. Core is the innermost part of the sun, and this is where nuclear fusion occurs. Nuclear fusion occurs here. So that's where the core of the sun is the source of all the heat and light. All the heat and light that we have in the sun, it gets generated at the core of the sun. Then after that, we have the radiative and the convective zones. Now, these radiative and the convective zones basically are the zones through which the energy keeps on passing on. The energy will move from the core to the photosphere through the radiative and the convective zones. So, so heat and light travel outward through these zones. All right. Now, after this, when it comes to the photosphere, photosphere basically is the surface. This is the surface of the sun. This is the surface of the sun. Just like how we have the crust, which is the outermost surface of the earth. Similarly, photosphere is, you can say in a manner, crust of this sun. But yes, of course, it is not solid like the earth. It is gaseous in nature altogether. Now, at the core of the sun, the temperature is very high. All right, the temperature is very high, and as we move from the core towards the outer part of the sun, what happens is that the temperature keeps on decreasing. Now, when it comes to the photosphere, what we basically see is that photosphere is where we see the surface of that the temperature would have come down because we have come away from the core of the sun. So at the core of the sun, for example, the temperature can be as high as 15 million degrees Celsius. Temperature can be up to 15 million degrees Celsius. And by the time we have come out of the core and then we have crossed the radiative and the convective zones in the photosphere, at the photosphere, the temperature is just 5 to 6,000 degrees Celsius. So from almost 15 million degrees Celsius, now the temperature has come down to just 5 to 6,000 degrees Celsius. Now, the outer part of the sun is the atmosphere. All right, it is the atmosphere, and the atmosphere of the sun is where we have two parts, chromosphere and corona. Now, corona. Do you know the meaning of corona? You have heard of the coronavirus. Do you know why coronavirus is called as corona, or why do we call this part of the sun as corona? What is the meaning of corona? Any idea? Yes, Tirtha, you are correct. Ravi, you are correct. Need more correct answers, please. So, corona, the meaning of corona is crown. The meaning of corona is crown. because the spikes that we have on coronavirus, they look like the crown of the virus. That's why it is called as the coronavirus. So similarly, when it comes to the regions of the sun, the outermost region of the sun in the atmosphere is called as corona, because it is like a crown of the sun. Now, when it comes to the chromosphere and corona, they are only visible during an eclipse. Whenever there is a solar eclipse, during the solar eclipse, you might have, if you have observed any picture, or in real life also, if you have observed any solar eclipse, then you will see that if it's a total solar eclipse, there is a ring-like structure that is visible. The complete sun is hidden, but there is a ring like a reddish ring like structure that is visible. So that ring like structure that you see is nothing but the corona. So it's like you can say the crown of a king. So that's why it is called as the corona. Now here's something very interesting happens, and that is in terms of temperature. As we are coming out of the sun, the temperature should keep on decreasing, because we have come away from the source of all the heat and light. So from 15 million degrees Celsius, it dropped to almost 1 million degrees Celsius between the convective and the radiative zone, and it drops down to almost 5 to 6,000 degrees Celsius by the time we are in the photosphere. And as we come out of the photosphere, the temperature should drop further. But something interesting happens, as I told you. Now the temperature starts to increase. Both in chromosphere and in corona, the temperature starts to increase again. And that is something which is very, very difficult for scientists to understand, that why exactly does something like this happen. That what happens in this particular scenario, that why is it that the temperature again starts to rise. So now what we see is that when it comes to the chromosphere, for example, chromosphere can have a temperature as high as even up to 50,000 degrees Celsius. Usually it's not up to 50,000 degrees Celsius, but it can have temperature up to 50,000 degrees Celsius. And then as you come to the corona can have a temperature of almost up to 1 to 2 million degrees Celsius. Up to 2 million degrees Celsius. So just imagine that this can have temperature of up to 50,000 degrees Celsius, and this can have a temperature of up to 2 million degrees Celsius. So now this is something which is very unique, that how is it that the temperature is rising all of a sudden? What's the reason behind this rise or sudden rise in temperature? The good thing is we don't know. We don't know the exact reason why does the temperature increase. There are various different studies that have been conducted. There are various theories behind why the temperature must be rising, but we do not really have a very concrete evidence to why all of a sudden temperature starts to increase again. And there are various studies that are being conducted. There was the Parker Solar Probe that was launched. So one of the studies that Parker Solar Probe is doing is about the atmosphere, to try and understand what's happening at this atmosphere. And even our own Aditya L1 mission. One of the primary objectives of the Aditya L1 mission is to study the sun, study specifically the atmosphere of the sun and all the activities in the atmosphere of the sun, so that we can gain some understanding of what really is causing this sudden increase in temperature. Why is this temperature rising so much all of a sudden? This we see that Aditya L1 is going to also study this as well. Now, when it comes to the sun, there are certain concepts which are also very, very crucial. There are certain events on the sun which are very, very crucial to understand. And three of the most important events are sunspots, solar flares, and solar winds. So let's try to understand what exactly do we mean by a sunspot, a solar flare, or solar flares, or solar winds. Now, first one, solar, or rather sunspot. Now, do you see that there are spots here? Do you see these spots? Now, these spots, these are called as sunspots. Now, what is the reason? Why do we even have these spots on the sun? Now, these are not spots. These are very large regions. These are regions which are larger than the Earth itself. Why are they looking like a spot? Why are they looking darker in color? The reason is that these are areas, these are regions which have lesser temperature as compared to the surrounding areas. So the surrounding areas can have a temperature in the range of 5500 to 6000 degrees Celsius largely. But these are areas which might have their temperature in the range of 3500 to 4500 degrees Celsius. So that's why here we see that the temperature is lower, and because of that, we see these spots. These That's why these look like spots. So these are dark, cooler areas that appear on the surface of the sun, and they have a temperature of around 3500 to 4500 degree Celsius. Now, when it comes to sunspots, sunspots form due to concentrated magnetic field lines that poke through the sun's surface. So what happens is that there are, in a manner you can say that they are formed because of magnetic anomalies on the sun. And then this is something that leads to lower temperature because a lot of particles are released from here. So what may happen is that some of the particles might be released, and that causes this area to have, let's say, lesser number of heat particles, lesser number of hot energy particles, and that's why this becomes an area which has lesser temperature, lower temperature as compared to all the vicinity, all the surrounding areas. So that's why it is called as a sunspot. Now, sunspots, uh, interestingly, they go through a cyclic event called as the solar cycle, which lasts for around 11 years. What it means is that if you have observed a sunspot at this particular place, 11 years later, 11 years later, the spots will appear at exactly this space, exactly where we are seeing a sunspot today. 11 years later, we'll see another sunspot appear at the exact same location once more. And that's why we say that sunspots, they follow a 11-year solar cycle. So these are sunspots. So these are nothing but dark or cooler areas that appear on the surface of the sun. Now, apart from that, we have solar flares. Now, these solar flares, as the name suggests, that these are flares. So there are high energy particles that are being released as flares. So that's why they are called as solar flares. Now, these are like big explosions that happen on the sun's surface, and they occur, I mean, they originate at the surface and they happen at the outer layer, that is the corona. So origin is surface, they are happening in the corona. So that's why they occur in the outer layer of the sun called as the corona. Now they are basically, you can say, sudden release of energy because they are like explosions. So suddenly an explosion happens and it again releases a lot of charged particles, a lot of charged particles. So that's why they can contain x-rays, ultraviolet light, a lot of energy and radiations are released. Sometimes charged particles like protons and electrons are also released. So it will happen, and that's why they will last for a few minutes to a few hours, and they are large explosions that happen, and they can also create beautiful auroras on the surface of the earth itself. So you might know about auroras, green colored light or pinkish light that you see in the north hemisphere or near the north pole or near the south pole. So they are called as auroras. So these auroras, they actually are created because, partially because of solar flares and also because of solar winds, the next concept that we are discussing. So when it comes to a solar wind, solar winds basically are magnetic winds that are released from the sun, which start traveling towards the outer solar system. Now these winds, just remember that they are a constant flow of charged particles, because we know that even in solar flares there are charged particles, right? Even that is a release of charged particles. But what is the difference? The difference is that solar winds are continuous in nature. They are continuous flow of charged particles coming out of the sun. Whereas in case of solar flares, they are like explosions, right? They are like explosions that are happening at the surface of the sun. So that's why they are also primarily composed of protons and electrons, but they also contain heavier ions, and they are emitted from the outermost layer, that is the corona. So that's why we see that it will lead to particles traveling outward, and that's why they also become the reason for these kind of events, which are called as auroras. So you might have heard of aurora, aurora borealis, and then there are aurora australis, right? Aurora borealis and aurora australis. So these two, they are phenomena like this, where you see the sky will turn green or sometimes pinkish in color because of the magnetic interaction between the earth's poles and the magnetic winds, that is solar wind or even solar flares, because that also has charged particles. So that's why these are created due to interaction. These are created due to interaction between the Earth's magnetic field and solar winds or flares. So this is exactly what we see in case of aurora borealis and aurora australis. Now, in this context, when it comes to this interaction, the interaction with solar flares or solar winds, they lead to these kind of natural phenomena. Now, why are they called as borealis? Do you know what is the meaning of the term borealis? Why are they being called as borealis? Any idea? Why the term borealis? Have you heard of the boreal areas or boreal forests? Do you know what boreal forests are? Hmm. Yeah, northern hemisphere, correct. So aurora, basically, you can say in a manner, is the Arctic areas. They are called sorry, boreal areas. So the boreal forests are boreal means Arctic. In a manner, you can say the northern hemisphere, the northern parts. That's why the Arctic area signifies boreal areas, and that's why we say boreal forests. So borealis is basically being derived from there because it is being observed in the northern hemisphere. That's why aurora borealis, green colored light that we see in the northern hemisphere. So that's why the term borealis is being used, and similarly the term australis because it's near Australia in the southern hemisphere. So now, when it comes to this kind of interaction, of course it produces these kind of natural phenomena, but at the same time, this interaction, these solar flares or solar winds can obstruct anything electrical, electronic, or magnetic, especially near the poles. All right, anything electrical, electronic, or magnetic in nature can be disrupted, can be obstructed. For example, we have even seen power failures happen whenever solar flares are very strong. Whenever very strong solar winds or strong solar flares they reach the earth, they can cause power disruptions. They cause disruptions in the communication lines. They cause disruptions in the satellite movements. So it all can happen because these are all electronic or electrical or magnetic systems. So they can actually face this problem. So that's why we see that this actually can happen. Read this question. This was asked in your 2022 paper. I'm launching the poll for you. It is an easy question to answer, and largely it becomes easy because of elimination. If you can use elimination, please mark your answers. Very good. 73% of you have marked the correct answer. Let me discuss this with you. If a major solar storm or solar flare reaches the Earth, which of the following are the possible effects on the Earth? First, GPS and navigation systems could fail. Can they fail? Yes, they can fail. Why? Because what are these? These are electronic systems. These are electronic systems. So of course they can fail. Second is tsunamis could occur at equatorial regions. First, tsunami. Second, equatorial. Where do we have the magnetic poles? The North Pole and the South Pole, not near the equators, correct? Equator is not magnetic in nature as much as the North and the South Poles are. So first equatorial is wrong. Second, tsunami. What is the reason for tsunami? Tsunami has largely seismic reasons, right? It happens because of seismic reasons, and that's why solar flares or solar storms, etc., they have nothing to do with tsunamis. Tsunamis have internal geological reasons. So that's why second statement is wrong. And this is where you get your answer. This is where you get your answer. So now third is power grids could be damaged. As I told you that anything that is electrical, electronic or magnetic in nature can be damaged. So this is correct. Intense auroras could occur over much of the earth. This is also correct. And this we saw after this question was asked. In 2023, we saw this this happening in Leh. If you have read the news in the Ladakh region, we actually saw this happen in 2023, and it is expected that this will happen here in this year also. Forest fires could take place over much of the earth. Why would forest fires occur? These are magnetically charged particles. It's not a blowtorch. It's not that heat is coming from the sun. No. Magnetic particles, electrically charged particles, they are reaching the earth. So why would forest fires occur? And if that was the case, why would only forest fires occur? We would all be roasted, right? We'll all be roasted alive if that was the case, but that's not the case. Orbits of the satellites would be disturbed, correct? As we discussed, that it can happen, especially near the poles. Shortwave radio communication of the aircraft flying over polar regions could be interrupted. Perfectly correct. That especially when it comes to polar areas, this can happen. So that's why the correct answer is C. Correct answer is C. Now, any questions if you have from all the discussions that we have had in the last 45 odd minutes? They've all searched and Googled because live data is provided. I hope that nobody has Googled the answers because you have nothing to gain out of it. It's not that I'm going to send you some money, it's just for you. Black hole's gravitational wave was reached, but how do we know that when the merger of black holes happened, and how do we know how long the distance is? See, the determinations are based on a lot of criteria. First, the strength of the gravitational wave is one of the ways in which we observe it. Secondly, when the gravitational waves travel, they also carry some information about their origin. So that also gives us certain ideas about where it has originated from. And thirdly, our observations with the help of various instruments and telescopes, they also give us ideas about where exactly they would have originated from. What will happen if a human enters a black hole? The human will never be able to enter the black hole. The human will be disintegrated into thousands of pieces. What do we have near singularity? So basically what happens is that the entire mass of the star, it gets concentrated at a very small space. So that's why singularity would have a very small area, and it would have a very strong gravitational field. So that's why just understand that when it comes to singularity, the area of singularity or the size of singularity, it would be very very small. All right, so that is why we see that, just imagine that something that was thousands of kilometers big, now it has reduced to some 5-10 kilometers, right? And now in this case, so the entire gravity of that very large object is now concentrated in a very small space, and that's why it has very strong gravity. Explanation written in Aurora slide. Yeah, this is it. Difference between corona and chromosphere. See, corona is the outermost area. It is much larger area as compared to chromosphere. Chromosphere is much smaller area and near the surface. So that's why it has very different properties from that sense. So can you explain gravitational waves again in brief? Gravitational waves, just remember that these are waves which are gravitational in origin, meaning that wherever you have something very massive, gravity is related to mass. Wherever you have higher mass, you have higher gravity. So this is the case here, that wherever you have very big mass, it can lead to the formation of waves that will come out of that area. On what basis the naming of black holes done? Not only black holes, but rather almost all the celestial bodies. There are certain nomenclature that we follow depending on where they have been found. What is, what is the latitude, longitude, and altitude? I mean, the three-dimensional space where they have been found in the part of the night sky. So there are a lot of things that we consider. A lot of names of different gods are also used. So it has a very big process altogether for the naming to happen. Please show the solar flares slide. This is the solar flare slide. What is the reason for green and pink color of aurora? The colors are largely because of nitrogen and oxygen. All right, nitrogen leads to the greenish tinge, and oxygen leads to the pinkish tinge. Uh, does the light bend near black hole? See, the space itself is bent. All right, the space itself is bent. That's why light bends near black hole. So what happens is that light, for example, we know that light travels in straight line, correct? Light travels in straight line. But here what happens is that the space itself is curved. So because of that, what happens is that the light, when it travels, it is curved. So that is why it gets bent. How much bigger is the black hole? It can be huge. I mean, it can, one black hole can have millions of earth inside it. It can be that huge. Sorry, I mean, massive star can be that huge. Black holes, they are very small. Black holes would be of the size of sometimes just, let's say, 10 kilometers, 15 kilometers, 50 kilometers, etc. etc. Sunspots is a land that was created at sun, like Earth is coming from molten magma. Not exactly, no, this is wrong. Who know I'll get Nobel Prizes? Sorry, you'll not get Nobel Prize for this theory. This is wrong theory. Please explain Indigo LIGO. Indigo LIGO is nothing but a gravitational wave observatory that we are building here in India, and the budget for uh, the setup has been now cleared by the government last year. Explain about sunspot magnetic field. See, what happens is that sometimes some particles or magnetic particles might be ejected out of the surface. So, as they are ejected out of the surface, they leave behind a vacuum, or rather a blank space behind. And that blank space, that's why it has a lower temperature as compared to its surrounding areas. So, that's why it is darker in its color. Is gravitational wave a vibration of the gravitational field? Not really, but you can say it is a kind of curve in the space, or you can say it is kind of a curvature in the space or wave in the space itself that is created, and that is why it travels from there on. Why we call them as aurora borealis and australis? Because if they use simpler names, everybody would understand, and that's why they don't use simple names. Boreal areas are basically in the north and Australia is in the south. That's why borealis and australis. They could have named them as northern lights and southern lights to make it easier for everybody else to understand, but unfortunately scientists don't work like that. Why these auroras occur only near the poles? Because poles have the strongest magnetic field on the earth. What is the impact of gravitational wave? Nothing as such. There's no impact that they create. Just for studies, for understanding, better understanding of the universe, they become important from that perspective. Please show the Indigo LIGO slide. Indigo LIGO slide. Yeah, here it is. As average stars have mass up to 1.44 times that of the mass of the sun, is there any mass of massive star? No, massive star is already above this. Above 1.44 is massive. Hmm. I think I've covered all the questions. Sorry, the connection got lost. Am I audible and visible now? I think there was some kind of an issue and the class got disconnected. So let's take a break. Anyway, I was about to take a break. Unfortunately, just about when I was about to take the break, this happened. So let's take a break here, and on the other side, we'll have start our discussion on planets. So right now it's 6:40. So let's be back by 6:50. Let's be back by 6:50 and continue our discussion. I see that a lot of you have been waiting here. Sorry. Welcome back, everyone. Now we move on to our next topic, and this is about planets. Now, what we know is that when it comes to our solar system has 8 planets in total. Now, when we talk about these 8 planets, first let's try to understand how do we even define a planet. What is a planet? So, planet is any celestial body, any astronomical body that is orbiting around the sun or orbiting around a star, which first we know that it is something that must orbit around the star. One criteria. Second criteria is it must be big enough to have enough gravity to force it into a spherical shape. We discussed this in terms of stars as well, that stars assume their spherical shape or almost spherical shape because of gravity. So something similar happens in this case as well, that they get their spherical shape because of the gravitational force that they possess. So first two criteria being, one, that it must orbit a star, and second, it must have almost, let's say, a spherical shape. Now for a very long time, these were the only two criteria to be fulfilled if you want to call any celestial body as a planet. These were the two criteria, and if there was any celestial body that fulfills these two criteria, it would be called as a planet. So that is where we were in the past. But then things changed. And then there was this third criteria that was added back in 2006. So in 2006, there was this third criteria that was added, that it must be big enough that its gravity cleared away any other object of similar size near its orbit around the sun. Meaning what? That for a celestial body to be called as a planet, it should not have anything in the vicinity which has its independent path. For example, we know that our Earth has a moon, and this moon revolves around the Earth. So then it's fine. But if our moon had an independent orbit around the sun and it was not getting affected by the Earth, then in that case, this third criteria would disqualify the Earth also being called as a planet. This is the meaning of the third criteria, that there should not be anything in the vicinity, and if there is anything in the vicinity, it must be orbiting around this planet. It must be completely affected by this particular planet, right? So this is how these three criteria were added. The third criteria was added. Now, why? What was the reason? Why did we have to call this as a planet? And the reason rather here was Pluto. If you remember, Pluto used to be a planet. There were 9 planets in the solar system, where Pluto was the ninth planet of the solar system. Now, then there was an observation, and this observation was about another celestial body, that is Aries. Now, discovery of Aries happened. Aries also was seen to be spherical in shape. Aries also revolves around the sun, and Aries was seen to be bigger than Pluto. So it is fulfilling the criteria. It is orbiting around the sun, it has a spherical shape, and size wise, it is actually bigger than Pluto. So why not call Aries also as a planet? So it should have become the 10th planet of the solar system. But then scientists also believed that the number of planets in the solar system should remain an elite list. That, okay, these are the only planets in the solar system, and we will not add new names to these planets in the solar system. So now they found this third criteria. Aries is very close to Pluto. All right, it is very close to Pluto. Yet both of them, they have their independent orbits around the sun. This was the point of disqualification for Pluto. That you have Aries, which is in the vicinity of Pluto, which is very near Pluto and has its own independent orbit. If Aries was surrounding, it was revolving Pluto, then in that case there was no problem. Pluto would have remained a planet. But unfortunately, that was not the case. And the scientists were also sitting free, so they thought that why not create a new criteria? And they created a new criteria for defining a planet. So then this third criteria was added, and both of these, that is Pluto and Aries, they now are called as dwarf planets. Both of them are now called as dwarf planets. Now, in this particular scenario, when it comes to dwarf planets, what celestial bodies are called as dwarf planets? The celestial bodies that fulfill the first two criteria, but not the third, they would be called as dwarf planets. All right. So that's why, unfortunately, Pluto now got disqualified. Pluto also had moons. So Pluto was fulfilling all the other criteria. But unfortunately, because of this, and largely this was because Aries was found to be bigger than Pluto. If Aries, let's say, was smaller than Pluto, perhaps this kind of discussion would not have started at the first place. But unfortunately, we found that Aries is bigger than Pluto. So why not call Aries as a planet? And this is what changed the entire story. Fun fact, later we found with New Horizons mission, etc., that Aries is actually smaller than Pluto. It was a miscalculation, a misobservation, because of which it looked like Aries was bigger than Pluto, but in reality, Aries was later found to be smaller than Pluto. So Pluto lost its planethood for nothing. It was a wrong observation on our end that got Pluto to lose its planethood, and it became a dwarf planet since then. And that's why there are people who are still fighting for Pluto's justice. If you even go to Instagram or you go to X or Twitter, you'll find that there are hashtags justice for Pluto, because many believe that for all the wrongs that were done to Pluto, it's time that we correct it. And the embarrassment that we were actually wrong, we have to accept it and give back planethood to Pluto. But it's not to happen yet. So that's why, just remember the concept of planets as well as the concept of dwarf planets. So all these, as you see, these are the dwarf planets. This all these are called as dwarf planets. Right? These are all called as dwarf planets. So just remember that these are the celestial bodies that are not able to fulfill the third criteria. And what is the third criteria? That there should be nothing in the vicinity. And if there is something in the vicinity, it should be revolving around this planet. But here the case was that both of them are independent. They are not getting affected by each other because they have both their independent orbit while being so close to each other. That is what disqualifies them from being a planet. All right. So this was the third criteria, that they should just clear their neighborhood. They should have nothing in their neighborhood. And if there is anything in the neighborhood, it should be surrounding this, or rather revolving this planet. Now, apart from planets, there are other celestial bodies also that we have in our solar system. For example, there are three very close celestial bodies: comets, asteroids, and meteoroids. So let's try to also understand what do we mean by comets, and what do we mean by asteroids, and what do we mean by meteoroids. Now, in terms of comets, comets are cosmic snowballs of frozen gases, rock, and dust, roughly the size of a small town. Roughly the size of a small town. Now, why we are saying this? Because when it comes to a comet, just remember that when it comes to comet versus asteroids, versus meteoroids, you'll find that comets actually are the biggest of the three. Comets compared to asteroids and meteoroids, they are the biggest of the three, and that's why they can have a large radius. So for example, their radius can be 5 kilometers to 10 kilometers to up to 30 kilometers can be the radius of a comet. So that's why we see that comet size can be bigger, and that's why they are actually bigger in as compared to asteroids and meteoroids. So they are, that's why they are called as cosmic snowballs of frozen gases, rock, dust. Now what happens is that this comet, it has a center, or which is also called as the nucleus, and this nucleus might have various different other things: dust, ice, carbon dioxide, ammonia, methane. So there will be all these things. There can be rocky material as well. So there can be rocks and minerals, and rocks and minerals, in a manner you can say that they form the base, and then there are dust particles, ionized gases, and all that. So rocks and dust, they become very very crucial part of the nucleus of this comet, and size of a small town. So why we are saying that they are roughly of the size of a small town? The reason is that they can be, let's say, 5 to 10 kilometers in their radius, and they can be up to 30 kilometers in their radius. They can be up to 30 kilometers in radius, and that's why these are comets. Now what we basically see is that astronomers, they think that comets are actually left over from the gas, dust, ice, etc., and the rocks that were initially formed in the solar system approximately 4.6 billion years ago. Now one of the most important thing about a comet is the fact that a comet has a tail, right? A comet is known for its tail. Correct. A comet is known for a tail. So you might, if you have observed any comet, something like this is what you would see, that it has a bright center and there is a long tail, right? There's a long tail that this comet has. Now, the second such object is an asteroid. Now, in case of an asteroid, asteroids basically are small, airless, rocky worlds. Now, why are we calling it as small, airless, rocky worlds? Because they do not have any atmosphere. They do not have any atmosphere. That's why we are calling them as airless. In terms of comets, comets have atmosphere. They have a hydrogen cloud. They have a hydrogen cloud that surrounds their nucleus. So that hydrogen cloud, in a manner you can say, it is like their atmosphere. So it basically, the hydrogen cloud would surround this. It would surround. It will be invisible. It will be surrounding it. So this is a hydrogen cloud. So that is basically what we see with comets. But in case of asteroids, there is nothing as such. All right. The asteroids, they do not have any atmosphere. They do not have anything surrounding it. They are very very small. They can be just like, you can say, half a kilometer in their radius, or even smaller. Most of them, they are even smaller than that. So that's why asteroids are very very small. On one hand, in comets we are saying that comets are what? Comets are 5 to 10 kilometers up to 30 kilometers in their radius, and in case of asteroids we are saying that maximum half a kilometer in their radius. So sometimes 100 meters, 200 meters, 500 meters, that's it. Now they are also called as planetoids or minor planets. And now in this particular scenario, when it comes to asteroids, asteroids can have various different types of composition. They can be metallic, they can be carbon rich, they can have various different types of minerals. So they can have, you can say, in a manner, anything that a planet could be made of. So for example, all the uh, minerals and metals, etc., that we find on the earth, they might be found on asteroids as well. So that's, but they are very small. So now when it comes to asteroids, there has been one mission with regard to asteroids which has been in the news. NASA capsule carrying first asteroid sample lands on the earth, and here we are talking about a mission called as OSIRIS REx. Osiris Rex mission that basically is a sample collection mission. So what we have basically done is that we have collected samples from one particular asteroid called as Bennu. Now this Bennu basically is a carbon rich asteroid. It's a carbon rich asteroid. And for the first time we've gone to a carbon rich asteroid and collected sample from there. So that's why it's a big mission. And now it has come back. It was launched back in 2016, and now it has come back. Then the third kind of celestial bodies are meteors, meteoroids, and meteorites. Now we'll try to understand first what do we mean by a meteoroid. All right. First we'll try to understand what is a meteoroid, and then we'll move on to what is a meteor and what is a meteorite. So a meteoroid is a small rock or a particle of debris in our solar system, and they range in size from just dust to around 10 meters in diameter. So maximum of 10 meters in diameter. So very small, right? They're very small. So even smaller than asteroids. They're even smaller than asteroids. So that's why just remember that comets are the biggest. Then most of the asteroids, and then meteoroids. All right. So that's why they're very small, and they can be just like 10 meters in their size. Asteroids, they can be almost, we can say, 200 to 500 meters, and comets are the biggest. Now, where are they found? Most of the comets, they are found beyond Neptune. All right. Most of them, they are found beyond Neptune. Uh, Beyond Neptune, there is one part, and we'll discuss about that where they are found. Then asteroids, you might know that most of the asteroids, they are found between Mars and Jupiter. Most of the asteroids are found between Mars and Jupiter, and meteorites are found everywhere. They are found everywhere, although most of them, again, they are found beyond Neptune, but they actually can be found at a large different kinds of places in this solar system. Now most of them, they are made of nickel and iron. I mean, when I talk about meteoroids, they are largely made of nickel and iron. They're very, very small in size. Now what is a meteor? When a meteoroid, when it burns up as it passes through the Earth's atmosphere, it is called as a meteor. So when we have any meteoroid that completely burns up at it as it passes through the Earth's atmosphere, it is called as a meteor. And when this meteoroid, if it is able to survive the falling, then it is called as a meteorite. So that's the basic difference between these three terms. Otherwise, composition wise and everything else, they are the same. Just that where are they found, based on that there is this difference. So that's why just remember that when it comes to a meteor, meteoroid is in space, meteor in the atmosphere as it completely burns up, and meteorite when it falls on the earth. And you might know that this falling of the meteorite on the earth led to something what we call as a mass extinction, right? This is what we call as a mass extinction. Now, what had happened is that a meteorite or bunch of meteorites, they fell on the earth, and as they fell on the earth, they released a lot of dust, etc., and covered the entire earth. And there were a lot of other problems, seismic problems that were caused, and that led to wiping out of more than 85% of the species that lived on the earth back then, including the dinosaurs. You might have heard that when there is a shooting star or a meteor falling, you should wish for something. So maybe they also did the same, but unfortunately did not work in their favor. So this led to a mass extinction. So what is mass extinction? When a huge number of or majority of the species that are residing on the earth, if they are completely wiped out, then in that case we call that kind of an event as a mass extinction. And until now, there have been 5 cases of mass extinction on this earth. 4 of them have been because of climatic factors, because you might know that earth goes through glacial and interglacial periods where the temperatures will rise, then temperatures fall, temperatures rise, fall, and so on. And that's why this is where we see that mass extinctions happen when there is a drastic change in the climate over hundreds to even 1,000 years. Similarly, today we say that there is a sixth mass extinction happening. Today, scientists talk about sixth mass extinction. Until now, there have been five mass extinctions, and in all of them, the causes have been natural. But in this particular scenario, it might be the case where we have an anthropogenic reason, because we see that how climate is changing with because of our actions, and that is something that is leading to another mass extinction event, which has been termed as the sixth mass extinction. So that's why we see that this is, just remember that these are some of the basic concepts. Read this question. This was asked in your paper. I think 2012 they had asked you this question. I'm launching the poll for you. Please mark your answers. Good. So 62% of you have marked the correct answer. Let me discuss this for rest of you. What is the difference between asteroids and comets? First, asteroids are small rocky planetoids. This is fine. While comets are formed of frozen gases held together by rocky and metallic material. We discussed this. So one is perfectly fine. Asteroids are found mostly between the orbits of Jupiter and Mars. Correct. While comets are found mostly between Venus and Mercury. No. What did we discuss? Mostly they are found beyond Neptune. They cannot survive near Mercury or Venus because there is such a strong force of gravitation of the sun that will not let this comet survive here. So that's why this is wrong. Third is comets show a perceptible glowing tail, which is correct, while asteroids do not. That's correct. So 1 and 3. So correct answer will be B. Now we come towards the edge of our solar system, where we have something called as the Kuiper belt. The Kuiper belt is something that extends from 30 to up to 55 astronomical units. 30 to 55 astronomical units. Now, in this case, first thing first, what do we mean by astronomical unit? How much is one astronomical unit? Any idea? How much is one astronomical unit? Yes, Ravi, you are correct. Shreya, you are correct, I think. Hmm. Yeah, right answers. So, one astronomical unit is almost 150 million kilometers. 150 million kilometers, which basically is the distance between the sun and the earth. So that is called as one astronomical unit. So that's why it's used to measure distances. Now here we are saying that it is 30 to 55 astronomical units, which is huge distance, right? Now in this case, when it comes to Kuiper belt, we see that New Horizons for the first time uh, came very close to the Kuiper belt. And as you can see that this is a belt that extends beyond Neptune, that this is where you have Neptune, and beyond Neptune the Kuiper belt starts. And that's why it is the house to a lot of smaller celestial bodies. A lot of comets are found here, a lot of meteoroids are found here, a lot of just dust particles etc are also found here. Pluto and a lot of other uh, dwarf planets, they are also found here. So that's why we see that a lot of smaller celestial bodies, they are found in this Kuiper belt. So what all? It has dwarf planets, it has meteoroids, it has comets, right? So all these things, they actually are found in this particular area, that is the Kuiper belt. Then the end of the solar system is something called as the Oort cloud. Now, Oort cloud, as you can see, it stretches between 2000 to up to 2 lakh astronomical units. Just imagine, one astronomical unit is where we are, the distance between the sun and the earth. We are talking about up to 2 lakh astronomical units, meaning 2 lakh times the distance between the sun and the earth. So that's the edge of the solar system. And this is where we see that it consists of a lot of ices such as water or methane, ethane, carbon monoxide, hydrogen cyanide, all these kind of things in their frozen state, because temperature here will be drastically low. And that's why all these, even if they are found, they would be found in their frozen state. So that's why, in a manner, we can say that Oort cloud becomes a boundary. It becomes the boundary between our solar system and all the other systems out there. So that is what Oort cloud is. So Oort cloud, in a manner, that's why we say that it is like a no man's land between one solar system and the next solar system outside. There is this question also that was asked in the context of, you can say, uh, trying to find life in outside our own solar system. So the concept of what we call as exoplanets. What do we mean by exoplanets? Exoplanets are the planets outside our solar system. All right. Exoplanets are the planets which are outside our solar system. So they would be called as exoplanets. So now there was this mission called as the Kepler mission. The mission called as the Kepler mission. And this Kepler mission was to find areas where finding life would be possible. All right. This was for finding regions surrounding a star where we have possibility of finding life. And this kind of an area is also called as the Goldilocks zone. This kind of an area where you have moderate temperatures, where it can be a habitable area for any kind of life form to exist. It is called as the Goldilocks zone. So that is where the question was asked. The term Goldilocks zone is often seen in the news in the context of what? So it is basically this: search for Earth like planets in the outer space, because we are trying to find life, right? We are trying to find life outside the scope of our solar system. That's why we are saying that this is where Goldilocks zone is. So this question was asked in your 2015 paper. So any questions from whatever we have discussed until now? Any questions if you have before we move on to our next section? Oort. Oort, basically, Oort cloud has been named as Oort because this was an idea, or this was an area that was also, as an idea, it was theorized by Jan Oort. Jan, Jan Oort was the name of the scientist who was behind the understanding of this concept, and that's why it was named after him. Comet part, please. So comets, basically we are saying that these are smaller celestial bodies which can have a radius of 5 to 10 kilometers or maximum up to 30 kilometers, and they are the ones where we see that they have a center which is made of a metal or some kind of mineral, and then they are surrounded by some of the ionized gases like hydrogen sulfide, carbon dioxide, etc., plus dust particles, and then there is a hydrogen cloud that surrounds this. And as they move, they actually have a fixed orbit around the sun. So as they move, they actually show a glowing perceptible tail. Previous slide. Previous slide. See, this is the previous slide. Third criteria, again, I am not able to understand. Please explain. Very, very simple. See, very simple. I'm saying that if there is anything in the surrounding area of any celestial body, then it disqualifies. There should not be anything. There should not be anything there in their neighborhood. If there is anything in their neighborhood, it should be revolving around that planet, which is the case with every planet. Earth has a moon. So moon is revolving around the earth. But if this moon was not revolving around the earth and it had an independent orbit with the sun, then even we would not call earth as a planet. That is what the third criteria is. That it should clear off its neighborhood. All right. It should completely clear off its neighborhood. Voyager mission. Voyager mission basically is a mission that we have taken to understand and observe the outer part of the solar system and move beyond that. So that is what the Voyager mission, even Voyager 1 and 2 both have been about that itself. Is there anything beyond the Oort cloud? Yes, there is. There would be other solar systems and everything else in the universe will be beyond Oort cloud. Oort cloud, basically, you can say, is the boundary of our solar system. So, of course, there is the entire universe outside our solar system. Please show meteoroid slide. Meteoroid slide here. Goldilocks. So just understand that Goldilocks zone is nothing but the habitable zone. We are trying to find areas where the temperatures are moderate, just like the Earth. So similarly, if there are temperatures which are moderate, which is neither very far from a star nor very near a star, then that part will be called as Goldilocks zone. Details about planet is required or not? Currently, there is nothing in the news, so I would say not required right now. What are quarks and anti-quarks? All right, quarks and anti-quarks are not related to our discussion at all, but quarks basically they form the basis of every particle that exists. All right, anti-quarks are antimatter of quarks, but quarks they form the form the basis of every particle. So all the protons, electrons, neutrons, all these are formed from quarks. Significance of Kuiper belt. See, significance wise, there's nothing, just that you can say that it's an outer region where a lot of smaller celestial bodies are found. Mean both should revolve around each other. No, moon, Earth does not revolve around moon. I'm saying that if there is any object in the vicinity, either it should not exist at all, but if it exists, it should keep on revolving around this planet. That's it. If moon was revolving around the sun, then the criteria would have been different. Yes, correct. You're absolutely correct. Kepler was designed to monitor about 1 lakh main sequence stars over a period of 3.5 years. During the first 6 weeks of the operation, Kepler discovered 5 exoplanets. This is correct, but there is no question here that you've asked. Can meteorite reach the surface of the Earth? Absolutely, it can. We just hope that it doesn't, but it can. It has happened in the past, it can happen again. Is there any planet which has life other than the Earth? Not that we know of, but although there are certain moons in our solar system, like Europa, etc., where we have found traces of water ice, for example, and that's why chances of small microbial life. Can asteroid move along with the orbit of a planet? Yes, they can. They are called as Trojan asteroids, about whom we'll discuss later. Not today, tomorrow. How Kepler mission is understanding Goldilocks. It's not understanding Goldilocks zone, it is finding Goldilocks zone. Why can't option A be the answer for the last question? Option A for the last question. The limits of habitable zone above the surface of the Earth. No, not the surface of the Earth. We are saying that around a star, around a given star, we are trying to find an area. Above the surface of the Earth is a very small sample size. So no, we are saying that okay, if there is a star, can we find areas where the temperature ranges are moderate? So that is a Goldilocks zone. So that's why A cannot be correct, because it is very specific only on the Earth and above the surface of the Earth only. Above the surface of the Earth, the limits of habitable zone exist. The atmosphere does support life. So that's not there. Difference between meteors, meteoroids, and meteorites. I just told you that meteoroids, they are found in space. As they burn up when they come near the Earth, pulled by the gravity of the Earth, if they burn up completely, they are meteors. And if they survive Earth's atmosphere and small specks, sometimes, or very small stones, they fall on the Earth, then they are called as meteorite. Range of the Kuiper belt, as I told you, 30 to 55 astronomical units is the range of the Kuiper belt. Hmm. So now, so until now, what we have discussed is the first part, and the first part basically was about space science, right? Where we discussed about the basics of the universe and basic understanding of the universe. Now we move on to the second part, and the second part is about space technology. All right. The second part is about space technology, where we discuss the various aspects of space technology, Like for example, how do we launch how do we launch a satellite? What are the various applications of satellites? What are the various different types of launchers, like what is a PSLV, what is a GSLV, etc. And then the role of ISRO and other missions. So these are the kinds of things that we are going to discuss in this particular section of space technology. Now, when it comes to this section, uh, the first thing that we are going to discuss is about how exactly do we make observations. All right, how do we make observations? What do we mean by ground based observations and what is space based observations? So when we look at these observations, try to understand how exactly the things are different in terms of